the people or your audience and your relatives are fine and also in a good shape. Okay, it's also important. Okay, but here, okay, this let's see if we can all see this. Okay, it's okay, and we'll see. Okay, so here the title of this talk is Dielectric multilayers as highly efficient broadband mirrors. It's summarized of some research I performed here at Low Murcia in collaboration with Professor Bueno, and also with two other people here in Salamanca University, Inigo Sola and Enrique Conejero, as well as Professor Vladimir Gasharian at Bakersfield University in the United States. No? So here is the index. First, I'm going to do an introduction about just talking about typical properties of a mirror, types of important mirrors, just to introduce the topic. Then I will focus on the dielectric multilayers, a special case where we have some, it's composed of different layers, of different thicknesses and index of refraction, and we can achieve a high average reflection. Then we will concentrate on the so-called unidirectional broadband reflectors. As it says, it's easy to understand that we want a very broad band, a very wide reflection band, and so this mirror can operate at a wide range of angles of incidence. No? To do this, we also want to optimize such mirrors, and we'll talk about the so-called phase compensation method, in which we can, as I say, optimize reflectance bandwidth and so on of such dielectric mirrors. And the principal use of such mirrors is in the case of the short pulse propagation, where we can be applied to reflect femtosecond pulses for uses in ultra-fast photonics. And then we will summarize our main results of this talk. So, introduction. The first question is, what's a mirror? It seems a simple question. It's an object that reflects light, but just a important point. In the case of the angle of reflection, is the same as the angle of incidence. It's the well-known Snell's law. Okay, so it's trivial from geometric optics that the angle of incidence is coincides with this angle. Okay, so but it's not so simple definition. So in this sense, just a diffraction grating we consider as a mirror. Or my students of optics 2, just remember what is this is a diffraction grating. It consists of a series of slits equally spaced, the distance d. Then we have an incoming beam of light, of white light, composed of several wavelengths. So we have different refractive orders. At n0 we have no light dispersion, but as we is the n, the refractive order, we have separation. Okay, well, this is in transmission, but we have also a reflection. These orders are also reflective. We have n0, n1, n2, and so essentially we have also a refractive index, but it cannot be properly considered as a mirror, despite there's some light that is reflected. Okay, so what are the basic properties of a mirror? So first, the reflectance R. It's the ratio of the reflected optical power to the incident one. It's trivial that this factor R is the ratio of the electric field for the reflected light in the incident light squared. Okay, so we have here that the reflectance plus the transmission equals 1. Okay, this is the well-known conservation law. Energy conservation law. Know that this term depends on the incident angle, wavelength, and polarization. For number of incidents, it doesn't depend on this polarization. Okay, so just as an anecdote, okay, this is some special cases, okay, just as a matter that there is no reflection, but okay, it has nothing to do with physics. It's nothing to do. It's not mirror. Okay, just you have to forget this topic. It's a scary topic, but there's no okay. There's no reflection. Okay. Anyway, more properties here. We have the phase shift. This is the optical phase change when comparing reflected light and incident light. And this is the delta phi. This is the phase of the reflected light minus the incident one, which also depends on wavelength and polarization. The simple case is the single boundary. And here we have a boundary between two different indices, N0 and N1, have a beam of incident light. So all of our students, what happens when N is less than N1 and the incident angle is less than the burster's angle? You all well know that the phase shift is pi radians. Okay, this is a simple case of when we might change the polarization of the incident beam. So it's okay, it's a simple case, and it's very important to manage this phase shift, as we'll see later when we talk about ultra short pulse propagation. Okay, more properties. Reflectance bandwidth, delta de lambda. What is this? Well, it's the limited wavelength where mirrors operate. So it also depends on polarization and incident angle. We decide we want a broadband reflectance bandwidth, as wide as possible. Here in this example here, we've got for a dielectric periodic structure, a cell with 13 alternating layers of silicon dioxide and titanium dioxide. This is, for example, the OR mirror. We have our incident light for natural polarization or whatever. We have our reflected beam and our transmitted beam. So here this directivity or reflectance versus the wavelength and the visible, and also here for the infrared. And for different polarization of angles of incidence, here we have what we call the reflectance bandwidth. We have near 100% or 1 reflectivity. This is what we want. So, this is what we desire to make this broadband as wide as possible. Okay, so remember the three properties, the three characteristics: the phase shift, reflectance, and the large bandwidth. So just to review some type of mirrors you all know. The first and more common is the metal coated mirror. Mirrors where the reflection is obtained from a metal coating. They are thin films of aluminum, silver, or gold, and are placed on a glass substrate. Okay, so mainly there are two types of this is the typical household mirror we got in the bathroom and so on, are the so-called second surface mirror. Here we have a thick glass, and here we have this is the thin metal layer, not silver or aluminum or whatever. Okay, so here we have the incident beam, in case partially reflected, a second reflection transmitted, also reflected, and here this is we have different reflections. Maybe the absorption in this case is greater than the second case, where this is the first mirror. In this case, there's just the thin metallic film is placed on the front, and the substrate, which is now the glass, it's called substrate, is placed behind. So here we've got just only one reflection. Okay, one in this substrate. Okay. Okay, a major drawback: the reflectance is well below 100% due to absorption. This is due to the metallic layer, and moreover due to the glass substrate in the case of the first case. Okay, so here I have represented the spin coefficient kappa versus the wavelength in nanometers. Just recall that this is the imaginary part of the complex refractive index of material. So for three different metals, aluminum, silver, and gold. Just remember that for a dielectric thin film, this kappa is 7 orders of magnitude less than for a metal. This for near, infrared, and so on. So this is one of the how can we avoid such absorption? Performing or designing very thin metal layers, even though there's a non-absorption. Okay, so for mirrors, the typical card mirrors, the convex and concave surface, typical for focusing laser beams or imaging applications. You know the concave mirror. Okay, here we've got inverted images, virtual images placed between the center of curvature and the focal point of this concave mirror. And the convex case, we have also a virtual image, direct virtual image, placed between the vertex of this mirror and the focal point. You will know this whole configuration. More mirrors. The deformable mirrors surface shape can be controlled with many degrees of freedom. So this type of mirrors, we can control the surface of this surface. It's well used when we want to correct the deformed wavefront of an incident wavefront. It can adapt the surface to the deformed, distorted wavefront. So we have here a reflected wavefront which is totally or partially corrected. Okay, mostly used for optics and for correcting wavefronts distortions, as I've commented. Okay, now more types. Because mirrors have different reflectance values for two different wavelengths. For example, here we have a mirror, it's called substrate, and here we have two different wavelengths. The shorter, here the shorter light, the blue wavelength and red. No? What does this mirror do? Essentially, it allows the the larger wavelengths to be transmitted and the shorter to be reflected. Okay, they are more used in harmonic separators in nonlinear frequency conversion, such as SAG, second harmonic generation, where we get two different blends and we want to separate these so different stream wavelengths. So it's other type, an important type of mirrors. Okay. Now we'll focus on the dielectric multilayers. This is the main of our research. Okay. Here we have it consists of multiple thin layers of different transparent optical materials. So reflections from interfaces can constructively interfere. And essentially, it's an interference process. Okay, so we can achieve very high reflectance over a certain wavelength range. The most common is the so-called Bragg mirror, where all the thickness are just the students are listening, again, 1/4 of the design wavelength. Okay? With this configuration, we achieve the highest possible reflectance. So let's review something of the Bragg mirror. Okay, here you have the multi-layer formed by 4 different layers with a refractive index N1, N2, N1, N2. Okay, with different widths, D1, D2, D1, D2. No? So here you have the incident beam of light. What happens when this condition applies? This is the phase thickness. So N1 times N1 equals N2 D2. And when it's equal to 1/4 of the incident wavelength, what happens? Well, it can be demonstrated. It's just essentially optics 2 that the path difference between, this is the first beam, LA and LB, goes through, reflected, partially transmitted, partially reflected, okay? So, as you can see, it's an interference pattern, it's an integral of lambda. And you know when this path difference is an integral multiple of lambda, we got constructive interference. So this is the highest possible reflectance we achieve under this condition, okay, for the Bragg mirrors. Now, what about the broadband electric mirrors? Okay, what are the uses? Okay, they mainly used in ultrafast laser, where this laser emits ultra-short pulses, durations of picoseconds, femtoseconds, and even attoseconds. They are the shortest, as well as far as I know, of shortest temporal width of such pulses. No? Here I have obtained this. This is okay. This Professor Bueno here has a very important laser that's this, a mod-lock titanium sapphire laser. It can generate pulses with less than 70 femtoseconds. This is the precision rate. This is the rate at which this laser keeps such 70 femtosecond pulse. So it's just about 70 million pulses per second. Okay? So it's a really it's impressionant. No, the tuning range it can operate in the visible and in the near infrared wave range, and important. They also mainly produce linear polarization light, horizontal. So as far as I know, no one produces circular polarization, but it's another topic. Okay. So the type is a mode-lock diode laser, 10 picoseconds of this spectral pulse width, repetition rate. It operates even for green color, also polynomial. So this is the type of femtosecond lasers. Okay, and here what it contains a sort of mirrors and directive mirrors we can generate, and also we want to control this beam with such a beam, which mirrors. So an important particular case, the so-called super mirrors. Okay? It seems impressive, but just that is a black mirror with an optimized for extremely high. Extremely high. Let's look. 99.999 and all lines you want within a certain wavelength ranges. No, that is the Ferri periodic interferometer. We will know we have two different active surfaces. Here we can have a thin metallic mirror, but also we have here a dielectric mirror with reflectances even more than this value. It's near 100%. A coordinated length, we have several reflections, then we have the transmitted, and the focus lens produce here the impressive fringe rings. You know that we vary this distance, this change gain, so we can use to measure very small distances. Here is the experimental setup of a Ferri-Perot interferometer. Here we have both reflective surfaces, the collimating lens, and here the focuses. Okay. Well, a very important case, the chip mirrors. What are they? Well, they are multi-layer directed layer where they have a variable layer thickness. Okay, here in the top figure, we've got a black mirror. It's a periodic layer, multi-layer. So we have N1, N2, N1, N2, but all have the same thickness. Okay. So when we got different wavelengths, the same that will differentiate between different wavelengths. What happens with a chill mirror? Here comes light left and has an increasing width layer. So the layers have an increasing width. It allows longer wavelengths to penetrate farther into the mirror than shorter wavelengths. So it's important because the main use of those chill mirrors is to compensate positive chromatic dispersion in transfer pulses. So, for example, here we see this configuration. We've got an ultra-fast laser, as previously shown. Okay, and they produce just 1 million pulses like this per second, million or even more. Okay, this is about the femtoseconds. When these chat pulses go through some optical medium, they experience the so-called positive chromatic dispersion. Why? Because the shorter wavelengths travel at higher velocities than the shorter wavelengths. So the pulses get broader. Okay. So how we compensate this broadening? With some chip mirrors. Because here, after several reflections on these mirrors, just remember, this part of the pulse goes back and this pulse goes in the front. So essentially we are compensating with a negative, they introduce a negative chromatic dispersion just to compensate positive chromatic dispersion. So we get It's also pulse compression. We get pulses as for these fast delays. This is the main use of such media. Okay. What about the other dimensional broadband reflectors? So I'm going to present some important works on this topic. Here is an important thing in science. Okay, seems a old-fashioned, but it's okay. It's an important paper. No, well, just remember. He reported high reflectivity for both polarizations S and P. S is the linear polarization perpendicular to the plane of incidence, and P is the parallel. Okay, from 10, this is here for the far, not the near, far infrared wavelength. Look, from 0 to even 80 degrees. We cover practically all the angle of incidence in multi-layer stacks of polystyrene and telluride. Okay. And then Lee and another in scientific report obtained a high reflectance over the ultraviolet for for ultraviolet for sapphire magnesium chloride triple layer. So here have a triple layer of different materials over an important reflectance. And even Slovak developed, this silicon-based metamaterial. It's a different case where we sorry, okay, sorry, okay, where obtained a single layer of metamaterial with a negative index of refraction. Okay, a high reflectivity at 1.5 micrometers. So this just as in the paper, as we know, we have also a type of the so-called unidirectional broadband reflectors. Here we have a sheet multilayer. Okay, but now look, is a decreasing width of cesium bromide and tellurium. And so the width is not increasing. This is a germanium substrate. Okay, and here's the plane of incidence, S polarization, P polarization. Okay, we have we want to obtain the reflectivity, the reflectance of this particular type of multilayer. So, how can we calculate the reflectance of such multilayers? Well, we use the transfer matrix method. What is this? Okay, essentially, it's a bit tough to explain, but essentially, we assign to each layer a 2 times 2 matrix. Okay, where we perform a product of such Q or N matrices, where this delta R are the phase thicknesses. Okay, for the Earth layer, and NR is the refractive index of this layer. Its width of thickness. This is the angle, the propagation angle in this layer, and lambda the wavelength. Eta R are the total optical admittance, and also depends on NR and polarization. This is the total optical admittance for the substrate. Okay, so it can be shown that the reflectance R is the product of this. This is the complex amplitude times its conjugate. Okay, so we have the real quantity, reflectance. Okay, just N0 is the admittance of the vacuum, and C and B are known by this product and reflectance. So just figure, we require a numerical analysis for 3, even more than 3 layers. Okay, we have 2 layers. It's some complicated. When we are managing 33, 4, 40 layers, it should be avoided. It should be treated with a numerical analysis. So this is an example now. I present some numerical results. Here we have 48 alternating layers of cesium bromide and tellurium. So here, this is for the density angle from 0 to 90 degrees, and the wavelength here for 4 to 12. We have here the mid infrared. Okay, so here we have the 2 multilayer I described previously. This parameter AL is the rate at which the layer thickness decrease. In this case, minus 22.2 nanometer layers. Okay. We see this is the transmittance. So there is 1 minus this is the reflectance. So we can see that this region will have a very low transmittance. So in other words, a very high reflectance. Okay, the bottom panel, we have the periodic multilayer, the Bragg reflector. It's a periodic multilayer in where AL is 0. Okay, there's no decreasing width. Okay, the red color means a very low transmittance. So we have here again, a very high transmittance. So here we have very low transmission. So we are achieving a broadband even greater than the Bragg reflector. Okay. If we change the value of this AL parameter, if we increase from minus 8.5, 22, we get, as the discard get blue, we got better reflectance values. No? So if we calculate the average transmittance, or figure, we calculate the average transmittance versus this value, okay, we obtain that the average transmittance decreases. It depends also on both polarizations, S and P polarization, until we get a minimum. This is what we want. We numerically calculate this minimum. Okay, just recall a minimum transmittance. Here we have a maximum reflectance. Okay, so that's what we numerically do. Just obtain the minimum of this average transmittance to obtain higher values of the reflectance. So for this case, for the optimum tube mirror with an average transmittance of 10 to the minus 7 is the average. Okay, so we've got for both polarizations, P and S polarizations, into the angle, wavelength in microns, we've got this result. Okay, just remember, blue and bluish and reddish colors means high reflectance band. Okay, bands. Yes, we can also see that it's better for S polarization than P polarization. It's obvious because you know that for P polarization, for angles near the Brewster angle, the reflectance is diminished. So always for P polarization, we get worse results than for S polarization. Okay, now how can we optimize such mirrors? Okay, well, now that we know that that decreasing width of the layers are, we can achieve grid reflectance values. What about when a short pulse is reflected on them? What about when a pulse is reflected on such a decreasing with the multilayers? So, not just important, not only high R values are needed, just we need smooth spectral phase because the pulse distortion is related to the so-called group delay dispersion, GDD. This GDD is just the second derivative of this phase respect to the frequency. So, constant GDD values, we obtain low pulse distortion. So remember, not only are high R values are needed, we only need that the mirror needs to have smooth spectral phases. So the GDD is a parameter to quantify how can we distort a pulse or not. So this is the phase compensation method, where it's a bit complicated, but I'm going to summarize as good as I can. Well, here we have two electric multilayers that are opposite in phase at a certain wavelength, the so-called reference lambda R. Look, here we call mirror A. Here we have different multilayers with different N1, N2, N3, N. This is the substrate with different thicknesses. For a mirror A, we want different mirrors B, which are, look, the same materials, say N1 is the same as N1, and N2, N2, but they are different thicknesses. They are opposite in phase, phi, at a certain wavelength. After some tedious calculations, we obtain that these, the thicknesses of such B multilayers can be obtained via the thickness of the multilayer. M is an integer, lambda R is an important parameter, the reference wavelength, and N are the refractive indices for this wavelength reference. So let's use an example. Here we have the spectral phase phi here, okay, and the reflectance R of two phase compensated Bragg mirrors, A and B. for 42 layers of germanium calcium fluoride. Germanium is the high refractive index, and this one is the low refractive index. So here, look, the red one is the phase, okay, for the A mirror. This is not a phase shift. This is called wrapping, because the numerical computation, when we compute numerically, the program does not allow phase values greater than pi or lower than minus pi. So this is not, I remain, this is not a phase shift. This is the phase should be like this. So this is a smooth phase, but limited, to this interval. When we choose this lambda r, the value, here we have the B multilayer, the black one, we obtain a broader, you see, a broader band, a broader spectral phase, also very smooth, no? And also happens with the reflectance. We have, this is the reflectance band for the A multilayer, A mirror, and for the optimized mirror, we have this huge, we have this ultra broadband reflector band for B mirror. This is for zero. This is the incidence of angle, normal incidence, and even for 45 degrees of angle of incidence. Okay, so with a good choice of this parameter lambda r, we optimize multilayer A. So this is an important parameter, lambda r. So both conditions are attained: broader reflectance band and smoother phase. So we can generate here, we can propagate, we can reflect pulses, ultra short pulses in such multilayers. So, for example, here we have the GDD as femtosecond square and the reflectance for in 42 alternating layers of germanium calcium fluoride, okay, for B multilayer. This is for B multilayer, for the 15.1, okay. Here's the incident wavelength. We are in the near infrared wavelength, and here the reference interleaved wavelength, lambda r. Here, red, here for reflectance, the red one, here we reflectance is near 1. So we have a ultra high reflectance. And here the green one, we take a constant value for GDD. So for this dashed line denotes that we have here, this is the lambda r. We got here the broadest possible reflectance one, wavelength, and here we have also a smooth phase, GDD. So for each value of this lambda r, we obtain an optimized GDD and reflectance. So we can select ad hoc multilayers. So just we change this lambda r, this is lambda r, for this you have another one, we can obtain ad hoc multilayers, just changing this parameter. If you are interested in to launch a pulse in center at this wavelength, we can choose this lambda r and generate an ad hoc elastic multilayer. So in other words, we have a family of different multilayers B, just changing this parameter lambda r. Okay, so but it's just the previous figures are for the reflector. But what about is it the best choice? Well, numerical result shows the following. Here we have again the reflectance of the GDD, the reflectance, the reference wavelength, and the incident wavelength. Here we have the chill multilayer, decreasing with multilayer. We have, as you see, more grid, more reflectance. So we have, as we stated previously, we have very high reflectance, but there's no correlation in bands, so they're not coincident. We want that also is this green zone should be coincident as long as possible with the green one. So here it's not the best choice. What's the best choice? Our investigation shown that the best choice are the low disordered Bragg multilayer, where we have introduced very low disorder in the phase thicknesses, low disorder, no total disorder. Okay, so we can see that this red region of high reflectance coincides the same practically with this greenish tone where we've got constant GDD values. So for each lambda r, okay, for this particular case, okay, we have a multilayer B. For this one, another one. So we can select as we want different multilayers B are as our choice. But the important case is the wide reflection band coincident with the GDD zone. Okay, so what about the ultrashort pulse propagation? So how does this optimized dielectric mirrors work with ultrashort pulses? So if now recall, we got Gaussian pulse A the omega. It's centered at a frequency omega 0 and has a full width half maximum FWHM delta the omega. This is the typical Gaussian pulse, okay? Delta the omega, omega 0, and its Fourier transform provides our time-dependent Gaussian pulse. This is the ft. No? What is Rn? This is the complex reflection amplitude. This is the Fourier form of this A the omega, okay? So how can we calculate this reflection amplitude? We calculate numerically via the TMM method. No? Just recall, we want long values of delta omega to achieve short pulses, short temporal pulses. No? So we should cover wide spectral ranges to achieve short pulses, seconds or even less. So present these numerical results for an ultra-short Gaussian pulse ft. It's calculated via the previous expression, reflected on a low disordered multilayer B. This is the reference wavelength we chose what we wanted because it's the best choice for this. This is the central wavelength of the pulse. We are not confused. That is the lambda r for generate over B multilayer, and this is the central wavelength of this ultrashort pulse. Look, 40 seconds, 40 femtoseconds. This is ultrashort pulse. So, yes, ft versus the time. For this normal incident, well, this is the incident pulse, and these are for S and P polarizations. You know that for normal incidents, both polarizations are indistinguishable, so are the same. As we change the angle of incidence, change the degrees, the angle of incidence of the mirror, we obtain now that for both S and P polarizations, they are, well, the pulse get distorted, is unavoidable. But it's a bit, if it's about 40 femtoseconds, it's practically the same. It's a little broadened, but up to 35 degrees, the pulse reflectance is greater. It's a good value of 0.9% up to 35 degrees. Right? It's a good result. So, in summary, a generic mirror is characterized by its reflectance, just record reflectance, phase shift, and bandwidth delta delta. So we have reviewed different types of mirrors, metal-coated mirrors, where the social losses are interlayer, curved mirrors, convex or concave surface, deformable mirrors, where the surface shape can be controlled, because mirrors with different air values for two wavelengths, electric layers form multiple thin layers of materials. We attain very high R and wide reflection band. If all the layer thicknesses are of a quarter of wavelength, we got the Bragg reflector, which is the highest R for a periodic multilayer. Okay, but mirrors are variable layer thicknesses with a periodic multilayer used to chromatic dispersion control to compensate in ultra-short pulses. The mirrors with decreasing width multilayers lead to the so-called omnidirectional broadband reflectors. Nevertheless, not only high R are needed, the mirror should also provide a smooth spectral phase for the short pulse to be properly reflected. The pulse distortion is measured in terms of the group dispersion delay, GDD. So important, we need high R values and near zero GDD values to achieve a good behavior of such mirrors with ultra-short pulses. So this can be done with the so-called phase optimization method, where we can select ad hoc, as we want, dielectric mirrors with specified characteristics. where we want negligible pulse distortion and high RPUs for femtosecond pulses. And thank you for attention.